Welcome to the Makerspace 101 drone making video. From Batch 3, Table J. The essential drone components of the drone are carbon fiber frame, propellers, Orange HD 5152 pair, electronic speed controller ESC Simon K30A, BLDC motor GT2205, a power distribution board 100 amperes BEC buck converter UBEC minus 5 volts 3 amperes, onboard flight controller Arduino Nano. The sensor is the initial measurement unit IMU MPU6050. Wi-Fi unit is a Node MCU ESP8266, and the transmitter is the Remote XY application for Android. Elaborating on the carbon fiber frame and the propellers. The provided carbon fiber frame is a lightweight, durable structure that holds the essential components of our drone together. It's made of carbon fiber, known for its strength to weight ratio, making it ideal for our purpose. Propellers create thrust for movement by spinning when powered by motors. Two propellers rotate counterclockwise while the other two rotate clockwise, with the tilt of propellers so adjusted that all push the air downwards. Elaborating on the ESC and the BLDC motor. ESCs consist of a controller, power, MOSFETs, and other circuitry housed in a compact enclosure. They receive commands from the flight controller, adjusting voltage and current in the motors accordingly, enabling precise control over propulsion. Drone motors convert electrical energy into mechanical power, spinning propellers to flight. Working with the respective ESCs and flight controller, Arduino Nano, they adjust propeller speed for stability. Elaborating on the power distribution board and the buck converter. The power distribution board is essential in distributing power from the main battery to motors and electronics. It regulates voltage, limits current, and protects against electrical faults, streamlining wiring and ensuring reliable performance. It regulates voltage from the drone's main battery, providing a stable 5-volt output for powering onboard electronics. It prevents voltage fluctuations, ensuring reliable operations. Elaborating on the onboard flight controller and the sensor. It is the core unit of the drone, responsible for stability and sensor data processing. It reads sensor data, executes flight algorithms like the PID controllers, and adjusts motor speeds to maintain stability. This unit gathers data by measuring orientation, acceleration, and rotation by combining a gyroscope and an accelerometer, which is vital to ensure stability, control altitude, and execute maneuvers. Mounted on the Arduino Nano board, it relays real-time motion data for precise adjustments. Elaborating on the Wi-Fi unit in the transmitter app, the Node MCU, a compact microcontroller with a built-in Wi-Fi, is a central control unit in our drone, enabling wireless communication, flight algorithms for stabilization and navigation, and telemetry data transmission. The easy-to-use interface and remote control help wirelessly relay the pilot's commands. Control signals are sent, which contribute to the feedback loop. The joystick allows for controlling the pitch, yaw, roll, and throttle movements of the drone during the flight. That is all. Thank you.
On day 1, during the primary assembly session, the team commenced building the drone from scratch. Starting with the fundamental mechanical components such as the basic chassis, each member actively engaged in assembling various parts of the drone, meticulously following the step-by-step instructions outlined in the assembly video. In the second lab, it was about the soldering session. All the team members observed the soldering processes and closely monitored as the ESCs, all the 4 units, Arduino Nano, MPU, Wi-Fi unit and the UBESC was meticulously soldered together by the TAs. As the soldering progressed, team members cross-checked the connections to ensure accuracy and reliability. The third lab was about the user interface deployment and calibration. In the third lab session, it was dedicated to refining the user interface calibration of the drone project, ensuring optimal control and performance during flight operations. The second step was about identification of the controls. We spent time identifying and mapping controls for roll, pitch, throttle, and yaw on the drone's user interface. This step ensures accurate control during flight maneuvers. The third step was about controller sensitivity check. Fine-tuning sensitivity is crucial for achieving smooth and precise control responses. We observed the tuning. Fourth step was about data observation. We observed and recorded how roll, pitch, and throttle and yaw values changed in response to different control inputs. On the fourth lab session, we focused on uploading 3 different Arduino sketches to enhance the functionality and calibration of our drone project. Set up code for controller calibration. The first sketch was dedicated to calibrating the controller. Despite facing challenges with the buggy calibration process, we persevered through numerous attempts until we successfully completed the calibration. In the second code was about ESC calibration. Our second code focused on calibrating the ESCs. We meticulously checked each motor of the drone individually, observed their relative rotation direction, and ensured they responded accurately to controller inputs. Third code was regarding the flight controller. The third sketch encased all the previous calibration steps. This code performed comprehensive checks to ensure that the controller, ESCs, and the other components were calibrated correctly, setting the stage for smooth and precise flight operations. These Arduino sketches played a vital role in fine-tuning and optimizing our drone's performance, ensuring that all systems work seamlessly together for a successful flight experience. In the fifth lab session, the team removed support from the landing gears and propeller guards to optimize the drone's performance. In the sixth lab, the final testing, and we attempted the drone fly. In the concluding lab session, the team focused on final preparations before testing the drone's flight capabilities. Initially, team members checked the calibration of the drone, ensuring its stability and functionality. Additionally, we fixed the landing gears and attached the propeller guards securely. With the drone ready for flight, the team proceeded to the hydrone lab where we were provided with propellers. In the presence of professors and RAs, the team attempted to fly the drone. However, despite our efforts, the drone encountered calibration issues, preventing successful liftoff. This setback prompted further troubleshooting and highlighted the importance of thorough calibration for future flight endeavors.
खोलना पड़ेगा जोर से खोलना बिठा के खोलना स्पैनर निकालो इसे स्टार्ट टाइटनिंग